Our goal today is to set up differential equations for an electrical circuit and to explore how different system measurements or outputs give rise to different responses. So here I have a real-life circuit, a temperature sensor, consisting of lots of individual components. This is a complicated circuit, so to get started, we'll consider the simplest circuits possible, those consisting of a single loop. We will analyze one-loop circuits and introduce the principles that eventually work for more complicated circuits as well. Here I have a one-loop circuit consisting of a single resistor with resistance R, a single inductor with inductance L, and a capacitor with capacitance C. Note that the letter L is given to the inductance because the letter I is reserved for current. L is in honor of physicist Heinrich Lenz. Let's dig into RLC circuits now. We will model the system using the 5-step process. So the first step is to draw a diagram of the system. We'll start with the power source, which is denoted by a circle with a wiggle, and we'll connect our components by wires, denoted by straight lines. The first component in our system will be the resistor, drawn as a zigzag. The second component is our inductor, which is denoted by a coil. And the final component is a capacitor, denoted by parallel segments. We then connect it back to the power source, and we have here our single loop circuit. Since all the components are in series, one after the other, we call this a series circuit. So these are RLC circuits in series. So the power source provides a voltage V. The resistor has a resistance R, the inductor has an inductance L, and the capacitor has a capacitance C. So the second step of the 5-step process is to identify all the variables and give the corresponding symbols. So the first variable will be the input voltage, which will be a function of time. So V is V of t, a function of time. The second variable is the current that goes through the system. So we'll denote the current by I of t, also a function of time, and we'll denote positive current as current that flows clockwise in this diagram. Since this is a series circuit, the current through all the components is the same. The other three parts that we can measure of the system are the voltage drops across each of these three components. So we have VR to be the voltage drop across the resistor. Then VL is the voltage drop across the inductor. And finally, VC is the voltage drop across the capacitor. And these are all the variables that we can measure in the system. So each of these components has an associated law that relates the voltage drop to current. So the associated law for the voltage drop across the resistor, which is a function of time, is given by R, the resistance, times the current, which is also a function of time. For the voltage drop across the inductor, we have that VL is equal to the inductance times the time derivative of the current. And finally, for the voltage drop across the capacitor, the law is slightly different. We have a relation between the time derivative of the voltage drop across the capacitor, and that is equal to 1 over C times the current. So note that R, L, and C are all constants, so these are linear relations between voltage drop and current. And these laws are actually a pretty big deal because it took generations of physicists to come up with them. And although they're not perfect, they serve as a great model that works for a wide range of circuits. So these are very important laws in physics. And the other thing that the circuit obeys is Kirchhoff's voltage law. So Kirchhoff's voltage law says that the voltage gain from the power source is equal to the sum of all the voltage drops across the circuit. So we have that V, our voltage gain from the power source, is equal to VR plus VL plus VC, the sum of the voltage drop across the components. And here, since we want to rewrite everything eventually as a single equation, we have to rewrite things in terms of time derivatives because we have VC dot showing up here. So a natural next step to take is to differentiate Kirchhoff's law. So we would get V dot is equal to VR dot plus VL dot plus VC dot. This way, we can use the relations that we have and plug them into the time derivative of Kirchhoff's voltage law. All right, now the next step is to declare what's the input and what's the system response of this system. So if we have an AM radio, for example, we would have the input being the voltage that is received through the radio waves and the antenna hitting, the radio waves hitting the antenna, and that would be seen here in the power source of the circuit. An output that we would be interested in, so a system response we would be interested in, would be the voltage drop across the resistor, as that signifies the output that we get through our headphones in an AM radio. So in our case, we will look at this system response of the voltage drop across the resistor. We could have chosen any of the voltage drops or even the current as our system response, but because we're interested in analyzing an AM radio, we'll take VR as our system response. The next step is to rewrite things in terms of our variable of interest, in terms of our system response. So we want to rewrite these associated laws in terms of VR. So in the first equation, I want to rewrite I, the current, so I of t, as a function of VR. So I'll divide both sides by R, and I get that the current is equal to VR over R. In the second equation, for VL of t, I note that I need the time derivative of the current. So I'll need to differentiate this part. And the only thing that's a function of time is VR. So we would get that VL is equal to L over R times VR dot. And finally, in our last equation, I have that VC dot is equal to 1 over C times VR of t over R. Now we have all of our variables as functions of the system response. The next step, in order to get a single differential equation for VR, the voltage drop across the resistor, is to plug in all of these expressions into Kirchhoff's voltage law. So let's do that. So we have the left-hand side says that V dot is equal to VR dot. So that's okay. It's already in terms of the system response. Plus the time derivative of VL. So here in the associated law, we have VL. We need to differentiate it, and we would get LR times VR double dot, because we differentiated this expression. And finally, we have to plug in VC dot, and we get 1 over C times R VR. So over here, we have a single differential equation with our input in one side and our system response in the other. And so one side only depends on the system response, and one side only depends on the input. the last step is to rewrite, so as we generally do, with the system response on the left-hand side and with the input on the right-hand side. For simplicity, I will multiply both sides by r. That way, each component will only have a single parameter, a single constant multiplying it, and we'll see that in a second. And I'll reorder such that the higher order derivatives appear first. So let's do that. So multiplying by r and putting first the highest order derivative. We would have L times VR double dot, so that's the first term, plus R times VR dot, plus 1 over C VR. And all of that is equal to R times V dot. Now we have system response on the left-hand side, input in the right-hand side, and the coefficients of each term is a single constant, a different constant, but a single one. So this is the differential equation for the system response for a given input. We can compare this equation to the mass dashpot spring system. So that equation reads that mx double dot plus bx dot plus kx is equal to by dot, where in this case I'm taking the forcing to come from the dashpot. So we can match each term and they all look the same. So these two equations have the exact same form, meaning that their solutions are of the same form. And that's a very important result, that RLC circuits can be modeled by the same equations that some physical systems are modeled. So what if we had chosen other system responses? What if we look at the system response across the inductor? And what about the system response across the capacitor? What would be the differential equations for each of these system responses? I'll let you work on that, and I'll come back with the answer in a bit.